Hello, my name is Martin Pike and welcome to this lecture from the Ada University course on Programming in the Large. The subject of this lecture is Ada typing, and together we shall complete a series of slides and then you will be assessed on your learning using some quiz questions. The slides will be split into three sections, the first covering range checks and overflows, followed by a look at primitives, and then ending with looking at derived types. The first section of this lecture will introduce you to the fundamentals of range checking and overflows in Ada. We understand that all high-level programming languages are ultimately compiled into machine instructions involving memory and CPU registers. CPU registers and memory are still the underlying representation of all Ada types, yet they know very little about the context of their binary content. In fact, it is most likely that the Ada types within your programs will be associated with a range that is much smaller than the range of your machine's underlying representation. Here we introduce an example of a type T1 that is given the range 1 to 10, and all objects of T1 can only have values within that range. The value is checked against the range at certain points in the program flow, such as during assignments, but is not checked on sub-expressions. The following code snippet provides an example of when checking takes place. Here we examine in more detail some specific examples of where range checks are performed in the program flow. Any kind of value assignment to an object, including that which is performed during explicit initialization, will cause the range of the type to be checked. Type conversion from one type to another, or during qualification of a value to a type, will also cause range checking to take place. And finally, parameter passing of an object into a procedure or a function will cause range checks to occur. Now we move on to covering potential pitfalls caused by overflows. Starting off with understanding that the high-level language program flow can produce temporary results in memory and CPU registers within the machine's representation, yet outside that of the object's eventual type range. Of course, if the value goes beyond the representation's range, then a hardware overflow will occur, but if that doesn't happen, and the resulting value somehow gets back in range, then the result will very likely be erroneous. This can cause a huge amount of confusion and often results that will differ each time the program is executed, making debugging almost impossible. Here is an example of some code that deliberately demonstrates how the compiler can be fooled into missing an overflow and performing erroneously. If we run through the following code snippet, we see the sub-expression v plus 10 will produce a temporary result that is outside of the valid range of an integer. V has already been explicitly initialized to the last permitted value in the range of an integer, so adding 10 to it should cause an overflow. However, it occurs in a sub-expression, and by the time the assignment takes place, the overflowed value has been halved and is now back in range. We must remember that range checking does not take place when the program flow performs sub-expressions. It is by chance that the final result is back within the valid range of an integer when assigned to v. No exception will occur here, yet the type system was circumvented. As you can see, the value printed out is erroneous. In a future lesson, we will encounter ways to avoid this situation. An Ada type is a unique entity throughout a program's source code and has attributes such as range specified at its declaration. Subtypes play a very central role in the Ada typing model and are a special designation of an Ada type. When a subtype is declared, it may be associated with additional constraints, but is certainly not a new type. And in fact, operations are permitted between a type and its subtypes, and possibly with additional checks. With that in mind, we see in this example a natural subtype of integer from 0 up to and including the last value in the range of integer. We also have a second subtype of integer called positive that has the range from 1 up to and including the last value in the range of integer. The object v1 is of type integer and explicitly initialized with the value 0. It is legal to then assign v1 to the object v2 that is an instance of the natural subtype because the integer 0 is in the range of the subtype natural. However, the last line of code is incorrect because the assignment of v1 to v3 is invalid due to 0 being outside the range of positive. In this example code snippet, we see a new type called day that is an enumeration with enumerates from Monday through to Sunday. Two subtypes of day are declared, one called business, which constrains the enumeration from the enumerates Monday to Friday, and a subtype called weekend that constrains day to the enumerates Saturday and Sunday. That's fairly straightforward, and we then come to a procedure called process day that accepts a parameter called d of the type day. The first line of procedure process day tests to see if the object d is in the range of the subtype business, and if so, prints out a string about waking up at 7 AM. Alternatively, if d is in the subtype weekend, then it goes on to use a case statement testing the explicit cast of d into the weekend subtype. If the entity is of the enumerate Saturday, then the string no time constraints is printed out, and alternatively if it's Sunday, then put line is called with the string go to bed 9 PM. Hopefully this demonstrates that types and subtypes are permitted to be used really as if they are the same type, but perhaps with a different view of the permitted values. The next section of this lecture covers primitives and how they are associated with Ada types. When you declare an Ada type, it can be characterized as an entity that has two sets of properties, including its data structure and the set of operations that apply to it. This isn't unique to Ada, and other programming languages like C++ and Java call these operations methods. Ada, however, uses the term primitives. Here is semantically similar code in Ada and C++ that shows an Ada primitive operation for the record type T called attribute function, alongside a C++ class definition with a public function with the same name, attribute function. In Ada, the relationship is implicit between the type and the primitive, yet it does require the equivalent of the C++ this or the Python self parameter. However, it can have any legal parameter name. There are general rules for how primitives are declared that involve which scope they are declared in and the type of the parameters. If you desired to declare an operation S as a primitive of the type T, then the declaration of S must be in the same scope as the declaration of type T. S must have at least one parameter of type T, and it can be any mode, including access, or it can be the return value from a function. Here we show a type T and 3 primitive operations. 2 procedures that show the order of the parameter of type T is not important, and a function that qualifies as a primitive of T due to its return type. It is possible for an operation to be a primitive of several types as long as the previous rules are always observed. This is demonstrated in the following code, where the procedure proc is a primitive operation of both T1 and T2 due to the scope and parameter type rules. It is possible for the compiler to implicitly create primitive operations for a type depending on the kind of the type. Here we see a numeric type T1 with a range 1 to 10 that would cause the compiler to generate at least the add and subtract primitive operations. Similarly, for the record type T2, there is an implicit declaration of the equality operation. These primitives can be used in exactly the same way as developer declared primitive operations using the fully packaged qualified operation name, or by having a use clause for the entire package. Often it is the case that use clauses are banned by coding standards in an attempt to increase readability. Without these, the fully qualified operation name, including the package prefix, must be used, again resulting in unmaintainable code and in fact reduced readability. An example of this is the procedure main in our first code snippet here, that is a verbose use of the primitive operations made worse by nested packages. There is an acceptable alternative in the form of use type clauses, which gives visibility to only the primitive operations of a specified type. The second implementation of procedure main here is much easier to read and yet has the same semantic qualities. Our final section of the slides part of the lecture covers one of the most powerful features of Ada, the ability to declare derived types. Deriving a new type can be performed by using the new keyword followed by the name of any non-tagged type. The following is an example of a new type called child being derived from an existing type called parent. The derived child type is able to benefit from any existing attributes of the parent type, including its data representation and any primitive operations. The code snippet to the right shows a numeric type called parent and a primitive operation called priv being declared ahead of a child type that is derived from parent. The body is able to pass a child typed object into the parent type primitive operation without any type conversion. This is because the child type inherited the primitive operation from its parent type. Please remember that although there are some inherited benefits, the new type is absolutely distinct within the type model, and type conversion will be needed when using non-primitive operations. Here we see package P declaring a numeric type parent with a range from 1 to 10, and then it is used to derive the new type child. Child will inherit certain benefits from parent, but it is a distinct type in its own right. We go on to declare a procedure main, which declares locally an operation called not a primitive. If we review why this is not a primitive operation, we can determine the reason as a breach of the scoping rules, as it was not declared within the same scope as the type declaration of one of its parameters. Procedure main goes on to declare 2 stack objects of type parent and child respectively. The procedure body makes calls to not a primitive passing the parent typed object naturally, but has to typecast the child typed object into the parent type for a second call to not a primitive. As we have seen, it is possible for derived types to inherit attributes of the type they were derived from. When the derived type is declared, it is possible for these inherited attributes to be modified in certain ways. There are certain restrictions though, and for example it is not possible to change an array into a scalar, or vice versa, because the basic structure must be preserved. It is possible though for scalar type ranges to be reduced during derivation, as we show in the following examples. The type int has a range from -100 through to 100, and both the derived types nat and pos go on to reduce this inherited range during their declaration. Any unconstrained types can also be specified in a derived type declaration, which is a very, very powerful feature. Here we can see an unconstrained array type called myArray being constrained when used to derive 10 elim array, and also when used to type a field within the record rec. While data structure attributes are inherited from parent types and can be manipulated during derivation, it is also true for primitive operations. To start off, it is possible to replace an inherited primitive operation with the derived type's own primitive operation with the same name. This is done by using the overriding prefix ahead of declaring the derived type's primitive operation. We can see in this example that root has a primitive operation called prim, and the derived child type has overridden this with its own version. A derived type can also add its own new primitive operation, and it is good practice to use the not overriding prefix ahead of any of these declarations. An example of this is shown here, where prim2 is a primitive operation of child but won't be a primitive operation of root. It is also possible for a derived type to specifically decide not to inherit primitive operations from its parent. This is done by again using the overriding prefix, but also ensuring the operation is declared as abstract. We have now reached the end of the slides section of this lecture. You should now have enough knowledge of Ada typing to complete a small quiz with questions designed to test your understanding. Good luck with the quiz. Our first question introduces a numeric type T1 with a range from 1 to 10. An instance of type T1 is created and named V, and it is explicitly initialized to the value 10. The body contains an assignment to V of the expression 1 plus V minus 1. Is the assignment to V correct? Click on the tick icon if you believe the code is correct or the location within the code you suspect is wrong. This code is correct. 1 plus V equals 11, but this is a temporary result, and we know range checks are not performed during sub-expressions. By the time the assignment takes place, the value 11 has been decremented by 1, and is therefore back in the range of the type T1. So there is no problem here. Question 2 builds on the code from the previous question, but this time the sub-expression is qualified as of type T1. Click on the tick icon if you believe the code is correct, or the location within the code you suspect is wrong. The code is incorrect. The qualification to T1 has changed what was a sub-expression into essentially an object assignment, which we know induces range checking. As 1 plus v is outside the permitted range of t1, a constraint error exception would have been raised. The next question presents two stack objects, both of type integer, that have been explicitly initialized to the last value in the range of integer. The body has two statements, the first of which doubles v1 and divides it by 4 before assigning the value back into v1. The second statement multiplies v2 by the result of dividing 2 by 4 and assigns the result back into v2. Click on the tick icon if you believe the code is correct, or the location within the code you suspect is wrong. This code is incorrect. The first statement has an overflow of the underlying representation and will therefore raise a constraint error exception. The second statement, however, is correct because of the operator priority and the correct use of bracketing. Our fourth question declares a type t as derived from integer with a constraint on the inherited range. Two stack objects are then created. The first, v1, is of type integer and is explicitly initialized to 0. The second, v2, is of the derived type t and it is explicitly initialized to the value of v1. Click on the tick icon if you believe the code is correct or the location within the code you suspect is wrong. This code is incorrect. Type t1 and integer are two completely different types, so a straight assignment from one to the other is invalid. Remember that derived types inherit nothing from the parent type other than the data structure and any primitive operations. The next question makes a slight modification to the code from the previous question, but I'm not going to tell you what the change is and leave you to identify it. Click on the tick icon if you believe the code is correct or the location within the code you suspect is wrong. This code is correct. I hope you spotted that the key change was type t is no longer derived from integer, but it is now a subtype of integer. This essentially means t and integer are of the same type, so direct assignments between them are perfectly legal. Question 6 now focuses on the use of subtypes using a more complex example. Here we present two subtypes, positive and natural. Positive is a subtype of integer with the range constrained from 1 up to the last permitted value of integer. Natural is a subtype of positive with the range constrained from 0 up to the last permitted value of positive. Click on the tick icon if you believe the code is correct or the location within the code you suspect is wrong. This code is incorrect. It will pass compilation, but a constraint error exception will be raised at runtime. The problem is with the range of the subtype natural. It includes 0, but the range of the parent type starts at 1. Subtypes are permitted to extend the range of the parent type, but not to reduce it. The next question is going to test your understanding of the rules for primitive operations. Package P1 declares a scalar type with the range 1 to 10. Package P2 derives a type T2 from T1 from package P1. The final package P3 declares an operation that has a single parameter of type T1 from package P1. The procedure main brings all three packages into scope and declares a stack object called v, which is of type T2 from package P2. The operation proc from package P3 is then called, passing it the stack object v. Click on the tick icon if you believe the code is correct, or the location within the code you suspect is wrong. This code is incorrect. The procedure proc is not a primitive operation of either the type T1 or T2, so cannot be passed an object of type T2 without an explicit type conversion. The next question introduces a primitive operation within package P1 called proc for the type T1. Package P2 declares a type T2 that is derived from the type T1 within package P1. The procedure main creates a stack object of type T2 and then passes it as a parameter in a call to proc. Click on the tick icon if you believe the code is correct, or the location within the code you suspect is wrong. This code is correct. We know that a derived type, in this case T2, inherits the data structure and any primitive operations from its parent type. The parent type in this example was T1, which has the primitive operation called proc. It is therefore safe to call proc, passing it directly an object of type T2 as proc has been inherited. Question 9 presents a more complex example, designed to test your knowledge of primitive operations. Package P declares two scalar types, each with a primitive operation called proc. The procedure body provides implementations of these primitive operations, and each implementation outputs a different value, either 1 or 2. The procedure main declares stack objects of the two types, and then makes a sequence of calls to proc, sometimes passing objects directly, and other times applying conversions. What text will be output? When you believe you know what the answer is, click the Submit button. The text output would be 1, 2, 2, 1. The type conversions have ensured that the correct primitive operations have been called for the eventual type of the converted parameter. Our final quiz question presents a hierarchy of derived types rooted at the type T1 that has a primitive operation declared called proc. Type T2 is a simple derivation from T1. Type T2 is also derived from T2 and replaces the inherited primitive operation proc with its own implementation. Click on the tick icon if you believe the code is correct, or the location within the code you suspect is wrong. We end on a high note, as this code is correct. T2 has an implicit derivation of the primitive operation proc, as it is derived from T1. The type T3 goes on to further inherit the primitive operation proc, which it then explicitly overrides. Thank you for attending this lecture on Ada typing as part of the course on programming in the large using Ada. I hope you have found it a valuable step in learning the Ada programming language, and that you continue on to the other lectures in the course from the Ada University. Thank you.